So, good morning, everybody. I am Professor Baladat, Assistant Professor, Mechanical Engineering Department. Would like to welcome you all in this final day, session 1 of Atal FDP on alternate fuels, which has been organized jointly by Automobile and Mechanical Engineering Department. So, for today, we have an international speaker who is a proud alumni of our college itself, ADIT. Now, I would like to request Professor Samarth Shelat to introduce our session expert. Over to Samarth, sir.
Hello everybody, a very good morning to all of you present over here for attending Atal AICT Faculty Development Program on alternate fuels. Myself Samarth Shelat, faculty from Automobile Engineering Department of A.D. Patel Institute of Technology, heartily welcome each one of you present over here. Today we have among us Mr. Jimit Mehta, quality engineer from Tesla Incorporated, for delivering a technical session on challenges with mass production of EV vehicles battery pack. I am also happy to say that he is one of our prestigious students. Now he is our alumni. Thank you, Mr. Jimmy, for accepting our invitation and coming to deliver a technical session. Now I would like to share a brief resume of our today's expert. He has done his diploma in automobile engineering from GTU in 2013 and bachelor's degree in automobile engineering from ADIT College in 2016. He has done his master's in mechanical engineering with specialization in manufacturing and design innovation from University of Texas at Dallas in 2018. He has also done various major projects and participated in Bahaja competition, which was held in 2015. Now, he worked as a quality engineer for Model 30Y HV battery manufacturing since 2019. Prior to that, he worked with the Tesla for 15 months across the general assembly and service team. Now, not much wasting of time to start our technical session. I request to Jimit Mehta to start the session. We will learn a lot from this technical session. Jimit?
Hey, thank you, Professor Samarth, for the introduction. Can you guys hear me just fine?
Yeah, it's fine.
Okay, yeah. So, yeah, thank you again, Professor Samarth, for the kind introduction. Good morning, everyone. Myself, Jimit Mehta, and today I would be taking the opportunity on speaking for the challenges that comes with the mass production of EV battery pack. It is to no one's surprise that the electrical vehicles and the battery manufacturing has been the topic in the recent years for the automotive industry. And it is believed that it is one of the major transition since the inception of this industry itself that we would be witnessing in this decade and the decade coming next to it. So definitely a very exciting time for all the automobile enthusiasts out there. I would be covering my presentation into a three-part, a very brief introduction for the need and the market growth for the electrical vehicles, what is driving that, and factors like that. Second to that, I would be diving into the supply chain constraints and the supply ramp that basically paces the whole industry growth at a level of tier 1 and tier 2 suppliers, how their design and their ability would define the growth rate of this industry itself. And lastly, I would be speaking on the manufacturing and the testing techniques that in general has been accepted by the industry regarding the manufacturing of this particular product. I would be skipping through this slide given that Samad sir had already given the introduction for it. But yes, I had the opportunity to work on this product from the very early age, especially with Tesla, given that it is one of the prime leader for this at this current moment. Before we dive into the next technical topic, I just want to make a very soft note that the rest of the presentation is my own research. It's might or might not be representing the view of my employer. I need to specify that given all the complexity around it. So the first topic before is the expected growth for the EV market itself. At the current rate that the market is growing, the rate at which the research and development is being done, and the amount that the consumer is now willing to spend for this technology, it is believed that all these factors, all in all, that by the end of this decade, the cost of manufacturing and high voltage electric vehicle battery and an internal combustion engine would be at par, which is also driven by the fact that towards the end of this decade, the overall production rate and the sales rate of this particular technology just at the light duty vehicles, excluding the heavy industry that is coming into it as well, would be around 40 million units. So definitely a long way to go and a lot of expected growth for this particular technology. The numbers had been changed in the last 6 months to 1 year, just because of the fact that the COVID era hit the industry really bad, which essentially diverted a lot of the financial funds that was going into the research and development for this technology into the different sectors, due to which the rate at which the technology would have grown is definitely delayed by a few years, but it is expected at a note at which this particular decade has started, that by end of this year, that pace would have caught up again and expected to have recovered the growth that we are expected. The main drivers and the motivation that is keeping everyone super motivated to keep working on the electric vehicles, and the reason that everyone is talking about it today, is mainly the environmental concerns that comes because of the very much awareness of the consumers of today, also about the global policies that are forming around this particular global warming, the pollution, and how the industry wants to take the ownership of changing and addressing this particular issue. There have been some uncertainty in recent times with the pricing and the supply of the gasoline itself, which is driving another factor and motivating companies to invest into this technology. And mainly, and the last thing is how the consumer attitude towards this topic has drastically changed and biased towards acceptance of this, and the need for us to have a sustainable future has finally been acknowledged. So given all this, there is definitely a promising future, but the path is not as straightforward as one would have anticipated going into it. The major hurdle that comes and immediate is the first thing is making sure that our suppliers, that is tier 1, tier 2 suppliers, are prepared for the growth that is this industry going through. And unfortunately, it seems to be, given on the recent constraints, that has come up as one of the major challenges for many electric vehicle companies to be not able to grow at the rate that they want to grow at. There are 4 major drivers that are constraining this particular constraint. Is first is the transportation of the material. This was something that was not at all expected to be an concern or a constraint at this point of the timeline. The sheer reason for it is we have the heavy air freights options available. We have very matured roadways logistics and the ocean logistics. And despite all that, what was learned in this amazing recent time was that anytime there is a small hiccup in the supply chain, which we did experience in this COVID era, is that it completely brings down the whole industry to a standstill, because there there are few components that are being sourced, for example, in an African continent. They are then shipped to an Asian nation and then shipped all the way to an European country, and then from there it would be shipped to some other continent altogether. So what that means is that even though that movement is quick enough, which is expected on a good day around 1,000 miles per day, had increased to approximately 5 to 7 days. Instead of 1 day every 1,000 miles, it has reached to like 5 to 7 days for every 1,000 miles. The reason for it was that a lot of countries at a different time period was shutting down for one reason or the other reason. There was not enough supply of the raw materials going to the suppliers itself for them to promote to the major manufacturers. So that's the transportation of the material topic. I won't be going in details in the coming slides, but wanted to mention given the big constraint it is. Next to it is the cell manufacturing raw material itself. Like one thing is the cell itself being a constraint and the supply demand, but next to it is the raw materials that goes into the cells. And lastly is the thing that has not only impacted the automotive industry, but all the power electronic industry as well in last 6 months. That is the PCBA and FPCA components. So diving into the first subtopic, that is the PCBA and FPCAs. So essentially, PCBAs are the printed circuit boards, and FPCBAs are the similar version, but instead of having a rigid structure, they are the flexible structure having the traces on the film-like material instead of the actual polymer layer itself. PCBA and FPCA supports the some form of battery management system technology in the HV battery. So it plays a very fundamental role for managing and collecting and controlling the voltage, the overall voltage of the battery and the individual cells, the temperature, the state of charge, and the depth of discharge that you expect at a battery level, the state of health of various defined measurements that you expect from and condition of the battery, and the current that you are drawing and outputting of the battery. All these factors are very essential for the performance and the safety features of an HV battery. And that's why having this component is very critical, and its functionality, without which it is believed that the feasibility of the HV battery might not be possible. It begs a bigger question is why suddenly the PCBA and FPCAs are like a constraint. They have been in an industry much before the EV industry started to grow. The reason for it is very basic and fundamental, that these components were mainly originated from the need of the other power electronics like our laptops, our cell phones, other smart home devices, the screen monitors, and those kind of products. It was not necessarily designed for the automotive arena. The design for this, like for the automotive, it's much more challenging, just because it has to be employed with other factors of the vehicles and how important the vehicle plays a role in general, wherein those products are our day-to-day and we spend more hourly time per day on those products, but essentially they are driven by a cost factor. They are not driven by the need of the reliability, because they are not governed for the safety or the regulatory basis, which the HV battery and the automotive vehicles are. So it does comes with a challenge which further reduces the ability for the suppliers to ramp up and design for the automotive thing. There are a few critical challenges that comes with the design of this particular component. The first is the volume and the surface area of PCBs. If you assume or if you look at our phones and our laptops today, they have got slimmer and slimmer today. So definitely the volume available inside the components is much smaller, even at the laptop and cell phone level, than it was. But what has happened differently for the HV batteries versus those components is the surface area of the HV battery has remained the constant. So my volume has just have reduced over the time because the packaging of the automotive component has always been much more precise than the otherwise at the overall volume percentage basis if you compare than the other components, wherein the other devices, they have reduced their thickness, but their surface area at the 2D level has increased. Like our screen size, our laptop screen size, they have drastically increased. So even if I have to make the PCBAs thinner, I can make them flatter and wide. So that is a trade-off and a difference between that we are finding a struggle for the HV batteries. Secondly is that the other components are not expected to go through the vibe conditions that the automotive or a vehicle is expected to go through. It goes through much higher frequency and the magnitude of the shocks um, than what any other power electronic or those components are meant to be. The same is applicable to the temperature as well. Most of the products are designed for to be operational between -10 to -20 degrees centigrade to around 50, 55 degrees centigrade. That is a normal operating temperature for majority of these components. But for an automotive, it has to be designed for something as cold as -40 degrees centigrade to something as hot as 65 degrees centigrade, given that the same vehicle that we manufacture goes to an super cold Alaska and Russian regions versus the same product is also driven in the hot and humid atmospheres like coastal areas and the Middle East and things like that. So definitely it comes as a challenge. The next is the precision of the operation that is required. Generally for this particular product and application, plus or minus 1% is the targeted accuracy. But for the HV battery, given that how at an accurate level you want your current, which is you usually control not at milliampere but at microampere level, you want the accuracy to be like as precise as 0.01 plus or minus percent. So it definitely brings in a lot of challenge. And the lastly, this component has to talk to so many subcomponents in the vehicle itself. That is your airbag, your seat restrainers, and all those things that all combined together make the harmonious network within itself to be able to function as intended. So owing to all this design change, it makes it even further more difficult for the options that are available in the market for the automotive industry to use the components that are there. And that's a partial reason that even though the PCBA industry had been there before the growth of EV industry, it is not able to catch up to the today's need. Coming to the supply constraint of that, the shortage started as soon as this EV market had started to grow. That was in the late 2017 to early 2018. And as we enter into 2021, that demand versus supply curve has just drawn apart more and more with each passing day. There are further more factors to it is there is not enough capex motivation for the suppliers to put in right now for the automotive industry. To put into the perspective, recently, because of all this global crisis that were out there, the PCBA suppliers had two options to go with. Either they keep on supporting the automotive industry, which has much less profit margin and a lot more competition, or they go with an in-trend gaming console where there had been cases where 100% of the PCBs for months were diverted towards products like Xbox and PlayStation, which were completely sold out for a month, which left the automotive industry dry for the need of PCBAs. So there is a lot of fight for the same PCBAs going into different areas. And depending upon who has a higher leverage, it is driving the demand right now. It was the recent IPC survey found that in February 2020 that at least 65% of electronic manufacturers were experiencing some component shortages to some degree, because there isn't simply haven't been enough capacitors, resistors, and other parts to go through, causing this demand and the supply curve to diverge further. The shortages weren't the only problem. So were the rising component prices, because the demand was increasing, the supply wasn't enough. So those component prices are rising. And all in all, what that basically says is that the automotive industry is expected to keep on growing for this component as it becomes smarter and smarter by approximately 28 to 32%, wherein the expected industry growth for the PCB is only 11 to 13% for the automotive sector. So right over there, it's only growing at a 50% rate than what the market needs. To put how severe this problem is, recently the companies like the Ford and General Motors, like literally 5 days back, they announced that they are cutting down their production by over 50% and shutting down their few factories because they don't have enough PCBAs to keep manufacturing the product that they want to. So this is how big of a problem statement it is in general for the automotive industry, and it becomes even more severe for the HV battery manufacturing, because the need for these components just multiplies by tens for the need of it. The next to it is the lithium ion cells itself, the very hard need of the HV battery. So again, it's the same concept, like the existence of this cylindrical battery cells has been there and commercialized since the late 20th century. And still, despite all that, today we do not have, as an industry, enough cell to meet the demand of what the market needs. Um, we have been using the lithium ion batteries in a different form in the functions like our phones, laptop, tablets, and etc. apart from the electric vehicles. Um, there have been different options like the lead acid and the nickel zinc batteries, which have a far more capability of doing the mass manufacturing, but it comes with its drawbacks, such that even if we are able to mass manufacture them, they are not perfectly suitable as of today in the cylindrical form for the HV battery manufacturing. If you take the lead acid battery for an example, we want to use the maximum energy density and the maximum energy that a cell has to provide. That is, you want it to charge to 100% and drive as low as to 5% to realize the maximum potential out there in form of range and power. If you go with lead acid battery, it is not capable of to discharge more than certain percent. And let's say that even if you do discharge it more than that lower threshold, it just does a permanent degradation to the capacity of the battery, which you cannot recover in the long term of an automotive, which is expected to be anywhere as low as 8 to 10 years of the operation. With the nickel zinc, the very fundamental problem with that is that it forms the dendrite, that is the the accumulation of the carbon and the metallic components on the terminus itself, which eventually grows in a manner that it can create an electrical short within itself, which certainly we don't want for it, something that is high voltage having this much ampere current with it. So that brings us to that while the lithium ion cells have been so far the favorite component of the cell in the cylindrical form to go with. It also comes with its design challenges. The primary for it is that we want to minimize the volume and the surface area of the cell. And that has been the driving factor that the industry so far has stayed with the cylindrical shape and has not tried to change the shape and the overall surface area of those cells, given that that thing has already been mastered by the tier 1, tier 2 suppliers. The supply chain had been completely set up for those components to keep on supplying. So that has been the driving factor of not changing those parameters. And we, like as an industry, they just want to maximize the energy density. So the amount of volume utilization has gone up, which is different from the AA, AAA, and the other factors of the cells that we use on day-to-day basis. The same as we captured for the PCBA boards earlier, is also applicable over here. the cells are individually individually mechanically constrained with each other inside a battery pack, and battery packs are towards the bottom of the vehicle, directly mounted on the chassis or the subframe of the vehicle, depending upon the manufacturing style, which basically translates into that particular component goes through a tremendous amount of direct mechanical stresses for a very long time. And it also goes through a lot of manufacturing stresses otherwise, just because cell is the first component that you put into the product manufacturing. It has to go through the whole processing before it is converted into the end product. So those cells have to be very sturdily designed, where even if your fit is essentially the same as the industry regular cells that we use, its design and the functionality expectation is completely different. So that's a challenge. Same temperature conditions is expected for the cells as well. The good thing or an advantage that we have with the temperature condition is that as more and more advancement comes with the electric vehicle HV batteries, it gives us the potential of um, creating the technologies like a heat pump and cooling systems, which basically helps to monitor the whole thing. So even if my outside temperature, let's say, is 70 degrees centigrade, the companies and the manufacturers have the ability to control it to the operating temperature they want. And then the lastly is the fail-safe systems that goes into the cells. Um, the cells usually, even at 30%, 40% of state of charge, they can go thermal. And when a cell of this capacity and this much dense energy goes thermal, it can produce a flame of 2 to 3 feet. So assume your AA battery cell creating a flame of 2 feet in all the three directions. It's it's pretty aggressive, so it needs to have a proper control of how it vents, how does it die towards the end of its life. So those are some design challenges for the lithium ion. It is expected that by the 2025, the total requirement of the lithium ion battery cells would be around 350 gigawatt hour. And as of 2019 end, there was a 200 gigawatt hour requirement. Just to put into the perspective, 1 gigawatt hour is approximately like a 3 million photovoltaic panels or 110 million LED cells. So this is tremendous amount of energy requirement that is forecasted, which industry is not set up exactly to achieve or deliver as of today. Um, it was in early or late 2020 that the companies like Audi and Jaguar and Ford, to some capacity, they had to cancel their build plan completely for the electric vehicles just because they did not had a supply for the battery for the lithium ion battery cells. So again, another constraint which is driving at a pace that industry grows at as of end of 2020, excluding the Tesla manufacturing capacity in-house, all the world manufacturers combined together did not had the ability to meet what the industry requires right now. Even if we don't use a single cell as elsewhere, 100% of them goes to the automotive industry. There is just not enough production worldwide right now to meet that demand. Um, the second topic to that I want to just touch quickly on it is the raw materials that goes into the lithium ion components itself. Um, one thing is, let's say that we magically create a manufacturing production lines that can pump out the battery cells at a rate that we want. But then second to it is that do we even have the raw material and the supply chain set up to provide that kind of deliverables that we can pump out the cells? And it is interesting that how the whole thing unfolds itself. So the lithium in general as a raw material, it's available everywhere. It is one of the largely found component or a mineral on the earth. But the problem is the quality of the and the reliability of a HV battery directly correlates to the quality of this product. It's like how much one is investing and getting the refined product and impurities out of it at a raw material level defines how well your HV battery is going to function and last in overall. Lithium is basically all of lithium, nickel, cobalt, manganese, and graphite are mined at a different capacity. Lithiums are generally found on the negatively charged post. Nickel approximately makes like 33 to 88% of EV batteries cathode side or the positive charge post. Cobalt is used morely like a mixture with nickel in the cathode side itself. And manganese is a substitute that the industry has gone to as a substitute to the cobalt itself. And graphite is the second largest by weight percentage that is used in the battery cells at different composition. It also acts as a good binder in the battery. The raw material constraint again goes to the same thing for that is that for 2019 for the demand that we were trying to achieve there were like 19 kiloton or the metric ton of cobalt, then 17 kiloton of lithium and manganese, 65 kiloton of nickel was sold just for the electric vehicles, but that demand is expected to go more by tenfold by end of this decade. Now there are two problem statement with the supply constraint for this particular um, constraint is that one, there has been an environmental concern for how much one wants to mine because more and more mines it indirectly creates some kind of an pollutions or the pollutants which again it's not exactly environmental friendly or we want to do with our conscious mind, so that is driving like how much these materials are being mined out. And the second is again because there is an uncertainty for the demand of this ones, it is not sure how much after a decade or two this would be needed. So the tier 1 tier 2 suppliers are not super motivated as of now to increase or invest into the capex. And let's say that even if they decide to invest into one of this technology or one of this mining today, it takes 5 to 10 years for any of the mine sites to be at full capacity of its utilization. So you start mining today and we might not see a result until half through this decade or by end of this decade from that mining site to be fully realized as in potential. So these are the three, all the main constraints that is driving into the pace at which the EV industry and the HV battery is growing. The next topic I want to talk about is the manufacturing techniques, which is also pacing at which rate we are able to produce or manufacture the HV batteries. So at a very fundamental, the HV batteries are a cell of arrays are put together into a module, and the modules are again clubbed together to make a battery pack, a high voltage battery pack. That is fundamentally how each and every product is designed for automotive HV battery packs. There might be slight changes from a manufacturer to manufacturer on how they are realizing the power that they want. Like one may connect fewer larger battery cells with a high individual cell capacity in series, and then they can be clustered into a module. The alternative is like multiple small battery cells with low individual cell capacity can be connected in parallel, and those ones can be connected to make a high capacity modules. So parallel connections ensure that you get a high capacity for your requirement, wherein series connections enhance the overall power that your HV battery is able to output. The four main challenges with the manufacturing is the new processes that needs to be developed specifically with the needs of the HV battery and its component. The design of the fixtures and equipment, the inspection standards are not exactly available in a market ready state as of this, given how early days this industry is still into compared to the IC engines that had gone through decades and decades of study and learnings for the automotive industry. The second is there is a special need of the safety precautions that comes for this particular factor as in also And the last is disposition of the non-conformance material. No matter how good your processes are, you can make a Six Sigma process that still creates and generates at a very low rate some defects. Those defects can or cannot be reworked, reutilized, and has to be disposition in a very sensible and aware manner. You cannot just dump it anywhere, given it's a live cells, the lithium and all with an electrolyte, they can be hazardous to the environment. Um, if one has to point out in at an high level what are the critical processes for this manufacturing, that would be the cell array arrangement and the assembly process, the interconnect process, and the handling and the inspection of this product, and the last is testing of it. So going into the first one is the cell array assembly process. Cell array assembly process is just a process that is a very first step of putting or placing the cell in the pattern that one needs or wants to achieve. Achieve in general. Generally accepted ones are the straight array cell array patterns, where your area, volume to energy density capacity reduces, but the manufacturing complexity also reduces with that. But if you use the honeycomb, the complexity is higher, but you get a higher energy density for those. So generally preferred and to go is a honeycomb pattern, even though it's difficult to manufacture. But the cell array pattern has also been used for the different applications. There has to be some clearance that needs to be maintained, given that there are some creepage concerns with this, which is true for the honeycomb and not exactly true for the straight cell array pattern. The other is the interconnect process itself. The interconnect process is basically connecting thousands of the cells to the circuit of the HV battery itself. To give an example, for Tesla Model S, there are over 7,000 individual battery cells that needs to be connected. There are over 4,000 cells for one of the other product. So connecting this many cells, it's super important and needs to be a very rapid things. So the driving factors for this interconnect process of connecting the cells are what kind of an electrical and thermal requirements you want out of this mechanical joint, what materials you are trying to join, as in the cell material and your bus bar material, what mechanical constraints or what mechanical requirements you want to have based on the constraints of the cell, and how much capex you want to invest into is the driving factors deciding which interconnect process you go with. Generally, there has been used is the ultrasonic welding, wire bonding, shouldering, laser beam resistance, and the friction steering. For lithium-ion cells, the ultrasonic welding, wire bonding, and the laser beam are the ones to go with. The ultrasonic is a direct material-to-material compression, where you do a high magnitude friction between that, such that the material fuses to create the mechanical joint that you want to achieve. Wire bonding is essentially the same. It works on the ultrasonic principle itself. The only difference is that it uses a third material to create a bridge between the bus bar and the your battery cells that you want to go with. It provides also the flexibility, which such that it can take much higher vibe in the field under the usage. And lately, there has been a lot of development with the laser beam welding itself, such that you put a substrate material on the top of the cell surface that you want to weld. You shoot a laser weld in a very controlled manner, but there has been some challenges as of today is the reflectivity of the surface that you are trying to weld with, how good your alignment is, and the air gap and the surface roughness. To put into perspective, even 100 micron of air gap between the two surfaces that you are trying to laser weld, it would fail the welding because the laser would just bounce off the surface and would not be able to fuse the material that you want. So those are the main challenges that you have with the interconnect process. The next is the handling and the inspection of the product itself. It is different because for the IC engine and other components with respect to that technology, it is very forgiving, wherein the HV battery components are not at all forgiving. For an example, if your battery cell has a cosmetic defect, which is anywhere upwards, even 50 to 100 micron, of depth. That is enough for that product to be not deemed safe for the use for the most cases. Might not be a true statement for all the cases, but for the most cases. Again, the fixtures, your production lines needs to be electrically isolated because these are live batteries, live cells during the manufacturing itself as well. Sorry. During the manufacturing itself, the ESD precautions has to be done. So obviously your manufacturing lines are built of metal. You cannot make it out of polymer or cannot 3D print it in realistic world. So it is a challenge of how electrically you ground them, how you isolate them to make sure your product manufacturing stays safe. And you need to maintain a large factory under a certain temperature, humidity, and also the vibration from end to end to make sure that your products are not. So all the solutions are not ready yet. So each manufacturer, each company is coming up with their own version of design for this, which is slowing down. So it's no more that they have to design the product. They also have to design how they are going to manufacture that thing, because there has been no market ready equipments for this, for the mass production. To put into the perspective for an architecture for the different vehicles, you can see that for an example, 85 kilowatt battery for Model S, there are over 7,000 cells. The first iteration of Tesla Roadster had over 6,500 cells. The easy part about that two component was it had a same architecture of module, but with newer version of Tesla Model 3, they have less number of cells, approximately around 4,000 cells, but it has two different kind of a module architecture within it, which further increases the complexity of how you produce it. And so is true for the BMW, Nissan, and Chevrolet Bolt. They have a slightly different approach to the cell type. They use the prismatic pouch and the pouch technology, which is still based on the lithium ion, but it's the packaging of that is very different than the cylindrical cells that is more widely used, even by the other manufacturers like Ford and Audi. I would like to now touch quickly on the last topic of the presentation, that is, what are the critical testing requirements for the HV battery? The reason for it is that given how early stage this industry is still into, the the companies are still learning how to test them effectively to make sure that the product that we are shipping to the customers are of the reliability standard that we need. And then based on those requirement needs, one has to go back and design those testers and fixtures, because again, we don't have a market ready solutions for this. So it's each company has their own unique standards, testing parameters, and things like that that they are doing. Of the three tests, one is the test for isolation, the other is test for continuity, and the last one is the functional test for your PCBs and HV joints after the manufacturing has been completed. So going into the first one is the test of isolation. The test of isolation is done based on two principles, is the HiPot testing or the insulation resistance testing. Sorry. Both of them are based on the Ohm's law, or rather, all the electrical testing that we are going to talk in this segment is going to be based on the Ohm's law itself. It's just the application of Ohm's law in a different manner. So the HiPot and the insulation resistance is basically you apply a high voltage to the conductors that you want to test, or the device that is under testing itself, and then there would be an external unit and the part of the equipment itself that would be measuring how much current is flowing through between the tester and the component that you are testing itself. And then based on that, it would calculate the resistance and try to make a decision based on your specification limits, that is this article acceptable or not. In generally, people mistakenly interchange the term HiPot and insulation resistance testing a lot, but there is a fundamental difference between the two. The HiPot testing is essentially you apply a voltage and measure the current throughout your testing time period. You do not allow the stabilization to occur on the device that you are testing. The reason for it is that when something arcs or there is an electrical current leakage, it creates a carbon deposition layer, and that carbon deposition layer can insulate it for an initial moment such that it can pass your testing if you're not looking at throughout the testing period. Where in insulation resistance, it is for the components where the current is expected to be absorbed for the initial phase before it stops leaking. And then after that, the final value of that test is only collected to make a decision whether that test unit is pass or fail. So both of them are basically an insulation testing. It's the application of it is slightly different. Um, the purpose of the HiPot OR and IR testing is to make sure that you receive the insulation in the high voltage components to make sure that your chassis, your pack, your other subcomponents are isolated for the manufacturing, for the serviceability, for the customers, and all the different needs. You don't want 400 volt and such a high amperage to leak somewhere and short someone, because that is essentially a life-threatening risk. There are two types of qualifications that is performed by this testing. Basically, qualification testing is essentially done at a design level, where you make sure that technically it is capable of preventing the dangerous arc or the current to pass through the product based on the insulation materials that you have used. And manufacturing testing is basically that you do on the 100% of the products that you are building. In both the cases, you apply multiple times magnitude voltage that you are expected to see in otherwise from the device itself. It basically, as we suggested on the earlier slide, that it tries to meet the requirement of having no spark, sufficient grounding, and the service and human and the customer factors is completely protected before it leaves the manufacturing line or automated manufacturing station. The last is the test for the continuity. Testing for the continuity is basically after you have made the connection of thousands of cells together, how do you ensure that each one of them is successfully done? For that, one has to make sure that they test an individual cell. Again, same Ohm's law is applied. There are different available market testers for this that are derived from the PCB technology, that is flying probe testing and fixed bench testing and fixtureless testing and etc. To go into more perspective, the flying bench probe and the fixtureless in-circuit testing are the ones that are used the majority of the time by the industry. So flying probe testing is nothing. The probes will, let me start this video in parallel so I can explain better. Okay, never mind. Basically, flying probe testings are built on the pogo pins itself. It's such that the pins will come down, connect on the each resistance or the sense location you want to test. It is as accurate of going to the 100 micron location in both X, Y, Z. And it can test up to more than 1,000 measurement points per second. So that is a tremendous speed, and that 1,000 measurements per second is inclusive of it moving, coming to the location it needs to test, collecting the data, making a decision based on that, reporting that data out, and saying whether it's a pass or fail. So this is also a very critical thing that has evolved with the EV industry itself in terms of testing. Towards the very end of the presentation, there was a lot of information that I shared. I went a little fast, but I want to leave a few topics, food for thought, around the mass manufacturing that would result into is like how one is going to recycle the EV batteries. Not today, but it's a topic that needs to be discussed, or the industry has to figure out towards the end of this decade or very early in the next decade, latest by. How does the next iteration of EV batteries are going to look like? Like, is cylindrical batteries are always going to be the solution? Or there might be some more like a solid state batteries that would be unleashing the new potential that can come out completely. The other topics are is fuel cell versus battery cells, the better, the charging stations that will come with it, and the service station evaluation itself, because the battery packs cannot be serviced at a localized global area. It has to be shipped back to a specialized location, which means that anytime an customer have an issue, you have to replace a battery pack, give him or her a good one, replace a bad one, send it, ship it to the reman location, and fix the problem, which is not exactly a challenge as of now for the IC engine vehicles. So those are just some food for thought, and I would like to end my presentation over here. If for the next few minutes anyone would have any questions for me, happy to answer them.
If any participants having the questions may raise their questions to the expert. Any questions from the participants?
Yeah, Mr. Jimit. Sanjay Patel here.
Hello, Sanjay sir.
Yeah, how are you?
All good.
Yeah. So, according to you, what is the biggest? I mean, if you want to summarize in what could be the biggest hurdle or challenge regarding electric batteries if you are implementing in electric vehicles?
I think the biggest hurdle, the immediate hurdle, can be in two parallel factors. Is one, on the manufacturing side, would be definitely the lithium-ion cells availability, and in parallel to that is also the consumer anxiety of not having enough range, which is a direct function of very limited charging stations that is available as of today. It just plays an anxiety role of how much they're willing to accept and how many lithium ion cells we have. So those two are going to be immediate drivers.
Yeah. Thank you. Thank you. Anybody else?
I have one question, Jimit. This is Subhash Joshi.
Hello, Subhash.
Yeah, see, the range anxiety for a city dweller, is it genuine? Because if he travels about 100 kilometers in a day within the city, is it still an anxiety of range for a EV user?
Not in a practical sense. It's more about the peace of mind that a consumer has, knowing that he or she has an availability of a gas station at any given point, which can be refueled within the 15 minutes or even less, like probably 5 minutes. But with an EV thing, just because it's an attitude change and the train of the consumer that would be needing over the time period, that's where the anxiety is still playing a role. But you pointed out it correctly that in practical sense, it really doesn't matter in the city traffic that even if you charge it at home every night, you might never need, or you will never essentially run out of the range, even based on today's technology, if you don't grow any further.
Oh, I have one more question.
Sure.
If the battery is discharging about 10 to 15% in a day, do we really need to charge every day?
It again depends. So one discharge factor would be that how much you are driving and what is your driving habit. The other discharge factor is the standalone discharge rate of the battery itself without consumption, which is a direct factor of the environmental condition that it is stored at. So it might not be needed, but it is very difficult to predict that one's HV battery would only drain 10 to 15% at a global level. It might be true for a small subset of the consumer, but not essentially correct for the large consumer.
I mean, even if a person uses 100 kilometers in a day, out of let's say 500, the range of the vehicle, example case, will he really need to charge even if the loss of charge is about 15% per day?
No, I don't believe if everything adds up, there is no other challenges. They might not need to charge um, if it's draining by 10 to 15% a day.
So this mindset of charging a mobile on a daily basis, we need to get out of it.
Agreed, which would only come through the training. It's more like pushing ourselves of accepting that technology, working on those things in general. I think it will only come with the time as more and more people accept this thing. It will become a trend with an awareness, and it is still more of an luxury item that people consider the EV vehicles. But the day it becomes an household item, I think that's when the trend would have caught up, knowing that it's not really a factor for me to make a decision how much battery charge I have.
So that means the initial people who are buying, they really have to become the ambassadors of the transformation in the thought process.
Yes, and I think that has what has happened for the last decade, at least. And that's why the companies are approaching that they come up with a luxury vehicle first before going to the economical version of the technology, because that way you are getting a free branding. Because if it's expensive, the mindset is that a light few people are going to buy that, which is going to provide you the free marketing that you need in the industry, which will draw the trend of an economical version, accepting the people to believe that, yes, this is something that can be done on day-to-day basis.
But in a country like India where two-wheelers run more than four-wheelers, will this logic of luxury work in India, or we'll have to find some new way to do it? What's your opinion?
It's tricky, right? I don't believe that how the economy of India is portrayed is actually true. To give an example, and it was surprising to me as well. I believe before I moved to United States, I was always like, oh no, India needs to have some economical version for acceptance of the technology. But for example, you take Ford Mustang. In India, it is sold upward 60 lakhs to 70 lakhs. If you consider the same vehicle that is manufactured in United States, that is of $30,000, if you convert that directly into the current INR, it is less than 30-40 lakhs. So Indians are willing to pay twice the amount for the same vehicle with a less technology, and it is selling more than a lot of supercars otherwise in India. For an example, when Porsche started in Gujarat for the first time, the company target was 11 vehicles per year. They sold over 30 vehicles on the day they launched, on the very day. So I don't believe that definitely the mass population is going to be a challenge, but I don't believe that it's exactly a constraint.
Okay, so the same theory will work for India also, right? Thank you so much. Thank you, Jimit.
Yep. I'm not sure if I still have the time or not. If not, then we can end over here.
No, we have time if you are available, because
I am.
yeah, that is the charm of this program. Mr. Subhash Joshi, who was asking a question, right? That he was our eminent speaker before a couple of days, or rather yesterday. So he was an